in all of the examples that we've looked at thus far, all of the discontinuities have either been infinite discontinuities or endpoint discontinuities. To me, the most difficult types of discontinuities with improper integrals are going to be the internal discontinuities because they're not necessarily obvious, right? So a fairly basic example of this is the integral from 0 to 33 dx 5 over x minus 1 dx. All right, so here's what we know about this. We certainly know that x cannot be equal to 1, okay? Just by looking at this, clearly the domain excludes 1. And so what we notice is that 1 falls within this interval, all right? So anytime you have a discontinuity that falls within the integral limits of integration, then that's an internal discontinuity. And what you're going to have to do is you're going to break it up into 2 separate integrals. And we haven't seen this before, all right? So I'm going to break this up into the limit as c approaches 1 from 0 to c, since 0 is the lower bound, of dx over the square or the 5th root of x minus 1. And then I'm going to add the limit as c approaches infinity, because it's still the same value, from c to 33, which is the upper bound of the exact same integral. So dx divided by the 5th root of x minus 1. Right. And this is completely legal. Okay, you could certainly break this up just because, and we saw this actually in our review of Calculus 1 stuff, is that we know that we can break it up as long as the function is going to be evaluable at that point. And eventually it will be once we integrate. Okay. All right. And by the way, this should be c approaches 1, not infinity. Sorry, I've been doing infinity so much that I forgot why it was infinity. All right. So now what we're going to do is evaluate the integral. All right. And let's just pick on one of the integrals. It doesn't matter which one. This is going to be a u substitution. So let's let u be equal to x minus 1. And du is going to be dx. And so we're just going to evaluate the integral. Now I'm just going to pull the integral off to the side, and then I'm going to plug in all the other stuff. So this is now going to be the integral of du over the 5th root of u. Okay, so we're just going to ignore all the limits of integration and anything that has to do with the boundaries, right? Or this is the same as the integral of u to the minus 1/5 du, which is the same as u to the 4/5 divided by 4/5, all right? And I know that there's a plus c if we're going through and doing it as an indefinite integral, but remember, we're going to plug it back in as definite integrals, and we're going to back substitute. So finally, we get 5/4 of the x minus 1 to the 4/5 power. All right, so let's just hold on to that for right now. And that's going to be what we're going to throw into these evaluated integrals right here. Okay, so just to make it a little bit easier on us for writing. Okay, so now this is the limit as c approaches 1. Right? So remember, we just evaluated this, okay, and that was 5/4 x minus 1 to the 4/5 from 0 to c, right? Plus the limit as c approaches 1, same thing, 5/4 x minus 1 to the 4/5 c to 33. All right. Now, I think most of us can clearly see, no pun intended, that when we throw in the 1 in for c, we get 1 minus 1, which is 0, and 0 to the positive 4/5 power is just going to go away. So it looks like anytime we plug in a c, it's just going to cancel out. All right, but we still have to contend with the 0 and the 33. So let's just plug it all in. Okay, so I'm going to now have the limit as c approaches 1. I almost wrote infinity again. And I'm just going to kind of combine all of this together. Okay, so we're going to have 5/4 of c minus 1 to the 4/5, okay, which we know is going to go to 0 anyway, minus 5/4 0 minus 1 to the 4/5. Okay, so we hold on to that, right? Plus, and in fact, what I'll do is I'll get rid of this bracket so that way we don't have to write the limit again. So now we're going to plug in the 33. So it's going to be 5/4 of 33 minus 1 to the 4/5 power. And now I'm going to plug in c again. So minus 5/4 of c minus 1 to the 4/5 power. And as we said before, once we substitute 1 in, that goes away. All right, so realistically, what are we left with here? Well, we're left with negative 5/4, negative 1 to the 4/5 power, plus 5/4, 32 to the 4/5 power. All right. Now, we know that this, if we evaluate that, negative 1 to the 4th is going to be positive 1, and the 5th root of negative 1 is going to end up being positive 1. So this just winds up being negative 5/4 for the first part. We know that the 5th root of 32 is going to be 2. So we really wind up with 2 to the 4th power times 5/4. All right. And that actually makes it pretty easy because that's 16 divided by 4, which is 4 times 5, which is plus 20. Okay. And again, that's just by, and you could certainly just throw that into your calculator if you don't trust my computations. But again, what's going to happen is this is just going to become 16 right here. All right, so this is 16, and then that becomes 4. 4 times 5 is 20, right? If we get a common denominator, that's going to wind up being an 80 over 4 minus 5. So really, we could write this as negative 5/4 plus 80/4, or 75/4. All right. Of course, if you don't trust the answer, throw it into Wolfram Alpha. Okay, Wolfram Alpha would never lie to you unless you type it in wrong. So let's just type this in just to verify. All right, and so if we do so, we're going to integrate 1 over quantity x minus 1 raised quantity to the 4/5. So be careful with your input. X is going to go from 0 to 33. All right. Now, hopefully Wolfram Alpha is smart enough, and Wolfram Alpha is plenty smart, okay? But unfortunately, it's not smart enough in this case to recognize that there's an internal discontinuity, okay? Oh, actually, I'm sorry. This should be to the 1/5 power because it's the 5th root. All right. So in that case, it was probably right. All right. But once again, notice that it gives you this number, but it also gives you like some complex root for some reason. Okay, so and that's because it doesn't take the limit. Okay, so there are times where Wolfram Alpha will not correctly compute. Okay, so but we know if we type in 20 minus 5 over 4, that's going to give us 75/4. Okay, so be careful with this. Okay, Wolfram Alpha doesn't always give you the right answer. Okay, it'll give you the algorithmic answer. All right. One more example before we finish up this video. This one's another sneaky sort of one that we have to break up. Okay, so we have negative infinity to infinity, arctan x dx x squared plus 1. All right, so this one's sneaky because we have to do a u sub to start, but we also have two discontinuities here, a negative and positive infinity. So here's how I'm going to do this. All right, I can break this up at any point that I choose. All right, I'm going to break it up at 0 because 0 is just like a natural midpoint between negative and positive infinity. So I'm going to write this as the limit as c approaches negative infinity from c to 0 of arc tan x That looks nothing like arctan x. Sorry. Let me see if I can write that correctly. So arctan x over x squared plus 1 dx plus the limit as d approaches infinity of arctan x over x squared plus 1 integral from 0 to d dx. Okay, so notice what I did there. I just broke it up into two separate integrals using some sort of value that's in between there. Okay, and I could have used, if I wanted to, I could have done this. I could have used pi, or I could have used, like, 55.1. All right, but we know that nice things happen when we try to pick nice numbers like zeros and ones, or even sometimes like e's or something like that. So I'm just going to pick 0 for this, right? Ignoring the limits of integration, let's just evaluate the integral. All right, so I'm just going to go ahead and evaluate arctan x divided by x squared plus 1 dx. To do that, I'm going to let u be equal to arctan of x, because the derivative of arctan is 1 over 1 plus x squared, which is precisely what we have here. All right, so this is now going to turn into the integral of u du, which is just going to be u squared over 2, which is going to be arctan x quantity square over 2. And now what I could do is I could just substitute that back in right here with our limits of integration. Okay, so just like we did in the previous problem. Okay, remember we just kind of pulled it off to the side. We didn't worry about once we broke it up. Okay, so this is now going to become, all right, the limit as c approaches negative infinity. Okay, I'm going to go from a to b. Okay, and actually, since we already back substituted it, we can just go ahead and skip all that. Sorry about that. We could just say that this is going to be arctan of x squared divided by 2, ranging from c to 0. Okay, so c to 0 plus the limit as d approaches positive infinity of the same thing. All right, from 0 to d. All right, now we're going to use our fundamental theorem of calculus. We're going to plug in. Okay, so we're going to have lim as c approaches minus infinity of, we're going to plug in 0 first. So arctan of 0 divided by 2. It should be arctan square, but for some reason, every time I try to write arctan, it doesn't show up. So arctan 0 square minus arctan of c square divided by 2. All right, so that takes care of that one. Plus, so now we're going to substitute. We have the limit as d approaches infinity. All right, and we're just continuing on. We have arctan d square divided by 2. And now we're going to substitute 0 in. So that was arctan of 0 divided by 2. And it should be arctan 0 square. All right, so let me erase this. 0 square. Okay, so this is where we have to be good with our arctangent function. Okay, and it might be helpful for us to look at the graph of the arctangent function, not the arctan square, but just the arctan function. So I'm going to go ahead and graph arctan x graph And here's our graph. Okay, let's go over, let's say, -10 to +10. Just so that way we can have an idea of what's going on with this. All right, so it didn't do what we wanted it to do, huh? But so arctan x graph. Oh, let me try this. -10. I didn't realize that I didn't type in the negative. Huh. No, that doesn't help out too much. Okay. Let me try to put it in the domain notation or the interval notation. Maybe that'll work. Nope. Okay. Nope. Okay. So let's just graph arctan of x. Frustrating. All right. Oh, or we can just scroll down here a little bit. Sorry about that. I want you to notice that at 0, it seems like that the arctan of 0 is 0. Okay, so we can see that right here from the graph. A little bit more difficult, though, is to see what's happening as the arctangent function approaches infinity and negative infinity. It looks like -1.5 and +1.5 respectively. All right, so that's kind of tough because, you know, we look at it and it looks like it's going to kind of converge to 1.5, but it's not quite. Okay, so this is going to go away and this is going to go away because they're both 0. And we're just going to substitute negative infinity and positive infinity back in. We have to be careful because we have some squares in here as well. So one thing to note, and I'm going to erase some of this stuff just so we have a little bit of room, is that we have to remember that the arctangent function has asymptotes. All right, so let me graph this, at least horizontal asymptotes when we graph it. All right, and this is one thing to keep in mind, not just for the examination, but also for the remainder of the course, and for those of you guys that have to take other courses, that the arctangent function does have these infinite limits and these horizontal sort of asymptotes. All right, so just graphing arctan. Okay, so this is our arctan function as best as I can. All right, so here's one of our horizontal asymptotes, and here's the other one. Okay, one asymptote is pi halves. The other one is negative pi halves. And that kind of makes sense because if you think of like the regular tangent function that does this sort of behavior, remember the asymptotes of the regular tangent function are in intervals like negative pi halves, 3 pi halves, negative 15 pi halves, etc. So what we know is that this limit as c approaches negative infinity of the arctangent is going to be negative pi halves. Okay. And then also as it approaches infinity, it's going to be pi halves. Okay. And that's from our graphs. Okay. So if we look at our graphs, we can figure that out. So what we end up with is the negative of negative pi halves square divided by 2. And then right here, we have the positive of pi halves square divided by 2. Ultimately, that just works out to be 0, right? They just cancel each other out. Okay, so this goes away, and this is going to be 0. All right. Now, of course, if you don't believe me, Wolfram Alpha always provides beneficial sort of help. All right, so we can integrate and remember our original was arctangent divided by 1 plus x squared. Okay, as x ranged from negative infinity to positive infinity. All right, and this should be 0. If not, then I have to redo the whole video. Or maybe I don't have to do anything if Wolfram Alpha decides to take too long. With the amount of time it's taking, we could have probably just solved it already by hand. Let me cut and paste it and see if I can just reload it. Maybe it's thinking too much. Oh boy. So even Wolfram Alpha can't handle this. All right. The way I suspect that this is going to be indeed a 0 is because I know 1 plus x squared is even, but arctan is odd. And so remember we had that rule that if you have the same bound from negative to positive, but we had an odd function that it was 0. All right. So I think this is going to work out to be 0 really easily. In fact, I'm almost certain of it, even though Wolfram Alpha is deciding to take an extremely long time. But again, what you guys can do is you can go ahead and just run it for a while and see if it gives you the 0 for this. One other thing you could do is you could just get the graph of this and see if it's symmetric at the origin. And if it is, notice that we would have, and this is the arctan function, not the arctan over x squared plus 1, but it would give you like something like this where you have below the axis and above the axis symmetry. All right. So maybe we can try Wolfram Alpha doing that. So maybe we can just graph arctan x 1 plus x squared. So let's see if Wolfram Alpha can handle that. All right, and it does. Okay, so notice if we were to go from negative infinity to positive infinity, notice like it has like this area that's below the axis, which would be the negative area. This would be the positive area. So at least it looks like it could be 0 from that. Okay, but I'm reasonably certain that all the work that we've done here is perfectly fine. Okay, all right. So again, another example to where Wolfram Alpha may not necessarily be helpful for us to be able to evaluate, but certainly knowing these techniques is going to be helpful. All right, so just a few more problems in this section, and then we'll be done working with our improper integrals.